Hello, my name is Shrikar, and actually, in this video or videos, I will talk about NXP, bare metal on NXP, and some basics of the NXP board. Actually, I'm working with NXP's I have FRDM board with IMX91. uh, this is my GitHub repository. In the manuals directory, you will got two manuals. One is application manual and another is user manual. So in user manual, you will see things like to get to know with NXP board. Okay. So for example, if someone uh, there is a switch SW3, then you will see here that okay, SW3 is here, like that. And in application manual, actually in application manual, you will get to know about how to write a bare metal program, right? You will yes, so this is some registers diagram, and at what bit does what thing. So here you will get that kind of description here. So this application manual is very large, around 4,000 or 4.5 thousand pages. So uh, let's go serially one by one. So in NXP board, I have this FRDM board. Actually, if I show this front view, yes, this one. So here to give power, you will use this C port. Uh, to interact serially via UART communication, we will use this debug uh, type C port. Actually, there are too many things you can see in manual. We will use this one USB-C port. I will tell this is some special kind of port to actually interact with direct internal storage of this NXP. And this is type A USB port, and this is Ethernet ports. And I think this is actually a microprocessor. So this is overall board. IMX91 is a microprocessor, and those are all peripherals for this processor. So let's quickly talk about the memory maps. Okay, so in this directory or repository only, there is memory map PDF. Okay, so here you will see that. Wait, uh, so there are just few notes written by me, and I have read manual, and according to that, I have generated this image using Gemini, giving credits to Gemini. Uh, so how memory map looks for our IMX91 and XP FRDM board. So you will see that from address this to this, it's boot ROM. Okay, that's hard coded ROM. We cannot change this. What is boot ROM task? So it just check the SW1 configuration. So these pins are SW1. Like you will see, this is 0, this is 1, this is 0, this is 1. Okay, and according to that, uh, NXP will choose the boot media. Like you want to boot from internal storage, you want to boot from external SD card, micro SD card, or you want to boot from Ethernet, like your kernel lies on the network, and like that. So in boot ROM, there is a code to just check this switch, and then go to that storage media. Okay, from that storage media, it will copy SPL, which is secondary program loader binary code. So it will copy to OC RAM. OC RAM is very small RAM on the chip, uh, and his task is to initiate the DRAM. DRAM is 2 GB main system memory. Okay, and so the RAM is initialized by OC RAM, and also that secondary program loader will load a program U-boot. Okay, so U-boot is like a bootloader for any kernel, or you say a Linux. Like in normal case, there are many bootloaders for x86, like for my laptop, like Grub. So U-boot works like that only. It will boot operating system for us. So first, a boot ROM sees those switches, these switches, go to that media, blindly copies first few bytes after some offset, and copies to this OC RAM. CPU will jump to this. It will execute this SPL program, which will initialize the DRAM and copy the U-boot to DRAM and jumps to that. Then our U-boot will be started. Okay. What U-boot does, before that you will see the expanded image for this DRAM. So our DRAM starts from 8 and then 7 zeros up to 8 Fs. Okay, so this is 2 GB, but from around 352 MB there is free RAM, then some 32 MB is secure or taken, and then again 620 MB there is free, and then the U-boot is loaded on this address. I got this by U-boot only, this address, and you would take around 50 MB, and then we have a free storage which is around 1 GB. Okay, not storage, my bad, the free RAM. So I will show exactly how all this will look. So if I connect all these pins to my laptop, like I have connected the power cable and debug cable to my laptop. I will connect this later, but after this thing, what I will does, I use picocom. Picocom is like putty. You can also use putty, but I like picocom because it prints on the terminal the output. uh, and I am setting baud rate dash B for baud rate as 115200. It is mentioned in the manual, user manual only, and selecting device. If you are on Windows, you will see like COM18 or COM11 like that. Okay, so if I click on this, it will just ask for my password. Okay, and if I enter, if I push the reset button, now where is the reset button? So if you see, there are three buttons, one this, another this, a third this. If you hold this button, the board will shut down. If you press this button, this one, then board will reset or restart, you will say. So if I press that button once, so it's restarting. Now I am hitting any key. I hit enter to stop. So what happened? You will say that after board has started, it loaded U-boot. This is some version, etc. And after that, it started down counting to automatically boot the Linux kernel. But I hit enter or any key, so I am now stuck on the U-boot. If I just enter boot, then I will boot to Linux. Let's show how it boots. So it will take some short time to actually boot to Linux. It is now booting to Linux, and it will take one more minute. Okay, so if you press just root, then yes, the Linux is booted. You will say if I do ls slash, so these are Linux directories, root directories. Okay, so I will hit, click that, or I will push that reset button again, and I will stop on U-boot, because now you saw that after U-boot boots, we are jumping to Linux, but now we will stop at U-boot and we will jump to our bare metal program. So how you will write a bare metal program, or how U-boot will boot to the bare metal program? So for that we have to read those application manuals. So if I show this, and there are memory maps also. From this only I got the values for this, like how much is for boot ROM, how much is for OC RAM, etc. So if I want to interact with GPIO, if I go to the GPIO only, Where is the GPIO? Wait, I will search for GPIO and go to wait. Huh. So general purpose input output, my bad. If you go on memory map and register definition subtopic of this GPIO topic, so here you will get the base addresses for 4 GPIO. There are 4 GPIO chip, each are handling 32 pins. Okay, and for each GPIO, there are these many registers like port data output. Or port set output, what it does, it will high the pin. Port clear output, it will low the pin, and all that. Port data direction, if we put a one corresponding to a pin on a bit of this port data direction, then or that pin will act like output pin. If we put 0, then it will be input pin. So like that only, I got those all information and made a library files and include file, those header files which we use in softwares like Keel or STM32 Cube ID. This is well maintained, or you will say there are very good comments for each code. Okay, so I defined those GPIO base addresses by looking at this manual only. Okay, and then these are registers. Obviously, after looking at these registers, and I just defined header files. If you want to see, you can directly see the code. On code, if you hover on the function, you will see what that function does. For parameters, what they want, like a pin, like pin number from 0 to 32. GPU write function, what it does, it like it will write on that pin, like you want to keep it high, you want to keep it low, and that all. And so there are multiple peripherals, one for interrupt control, general interrupt controller, one for GPIO, one for IOMux. IOMux is used for, see, now actually in NXP's world, they say those physical pins as a pin, but for GPIO, there are pads. Like we say, right, that GPIO 1 have 32 pins, but they say GPIO 1 have 32 pads. They are just saying it as pad. And for physical pin, metallic pin to which we connect the jumper cable, they said it pin, normal pin. So we will say that GPIO 1 have 32 pads. Okay, now that pad is mapped to a physical pin. Okay, but it can also happen that we can map UART's TX pad to a pin. Okay, to a physical pin. So a physical pin can be mapped to multiple pads. Okay, for that you will read the IOMux chapter of this application processor. So after that, like you will set pads alternate mode. Actually, I think it should be pin because we are setting a pins alternate mode, but that's okay. Um, okay, so what will be the process to start an application? Okay, I will show a demo, full demo. So first, you will open terminal in this directory only, and you will see there are only 3 applications: hello world, little os, and sonar proximity. So if I just run make command, so there is a make file which actually handles the make commands. You will see the recipes for make commands. If I enter this make init app is equal to demo, so it will create a app called demo. Here you will see that if I enter this, yes, it created that demo app. In demo app, you will see files like include. Actually here, when uh, developer will work on this demo app, it will have some header files. It will put those header file in this include folder. It will have some source files. It will put those source file in the source folder, and at the start we are giving a basic template. He can obviously he can change this basic template. There are a main function. So when we'll run this binary on the NXP, it will start running from this main function. And the hardware initialization, like I want to initialize UART1 with baud rate this, and this is a clock given to the UART. I want to initialize the GIC for interrupt handling, and I am providing a vector table. Now concept of vector table on this NXP is a little bit different because it is a microprocessor, not a microcontroller. It is A series ARMS chip, not M series. In M series, actually in vector table we have only addresses, but in A series actually we provide actual what we will say interrupt handlers. So like if you see the vector.s, uh, you will see how we are providing actually what to do. So suppose there is a trap occurred which is due to an IRQ. Okay, so it will automatically jump on this address only to handle this IRQ. And what we are doing, we are just jumping to trap IRQ. So what is this trap IRQ? So trap IRQ is defined here. So trap IRQ is just move one to the X3 register and branch to common trap. So what is common trap? Common trap is just this recipe to just do nothing and hold CPU. We will use common trap mostly to print what happened exactly, like when that crash happened or the trap happened, what exactly trap happened, we can print that to debug. And yes, that's all. And okay, now we will see how you will compile this. You can compile from here only, like make and just app is equal to demo, like this. Or you can, if you cd to that, like cd app demo. Now I'm in that demo directory. If I show all files, show here there is an include directory, a linker script, a make file. In source there are 3 files. Okay, like this only. Okay, if I run make here, it compiled all the files and it put in that in this build directory. Here in build directory, if I ls build to see what files are in the build directory, you will see this demo.bin. So this is a raw binary. So we first compile those C files using a cross compiler actually, because the binary is will run on the NXP board. And then we got this elf file, which is executable and linkable file, demo.elf, and we converted this elf to this binary. Okay, you will see all the process here actually. Okay, uh, so here in this line we converted demo.elf to demo.binary file, and we need this binary file. Okay, so how we will put this binary on the NXP board. Okay, now here we will need that special USB type C. Okay, you will connect this USB type C to your laptop only. Okay, then go to U-boot. Okay, hit enter and just pause on U-boot. There are many commands. If you just type help, you will got too many commands you will run on the U-boot. Please look into this. And after this, if I run the UMS command, okay, I will just type UMS, then it will tell how to use actually. So UMS, then USB controller, UMS USB controller 0 for this USB type C. Okay, and then device type MMC for storage device, and which, so zeros. Now as I told, we can use a storage media which is inbuilt, which is eMMC, or we will call it MMC 0, or micro SD card. Okay, we will call it MMC 1. So here I will use the internal storage MMC 0. Okay, so they give example also, but if I run this, you will see yep. So here two devices are mounted on my Ubuntu. Okay, so now the internal storage of the NXP board is acting like a USB pen drive for my Ubuntu. So I will just copy paste the files to it. Before going to that, there is disk utility in the Ubuntu. I will show how internal storage is look like. So first I will just zoom in, scale it to 2000. Okay, keep changes. Huh. So you will see the 7.8 GB internal storage of the NXP board. So there is a first 8.4 MB free space. Don't alter this free space. Actually, the code of U-boot and that SPL lies here. Then the partition one, which is a boot, it named at boot. Then free space, I don't know why it is there. And then root partition 6.9 GB. And then there is also free space. I don't know why it is there. So actually you will see the boot partition, root partitions are mounted. So in boot partition you will see the image. This is actually binary for a binary file for a Linux kernel which U-boot boots. Okay, and these are just like device trees which Linux kernel uses. Okay, and the another is root directory, which is a root directory for a Linux. So you will see this bin, boot, dev, etc, home, etc directories here also. Okay, so I will come back to now 100% zoom. Okay, so we will create this free space for keeping. We will use this free space to keep our binary files. So first for that we will create a partition. Okay, in allocated spaces, and we will just extend partition. No, next volume name we will call it Baremetal. Okay, just Baremetal. Erase, I don't want to erase. And yes, that should be fat file system. Why fat file system? Because or U-boot have compatibility to read fat file systems. Okay, you will see the fat ls, fat info, and all those commands. So I will format this internal storage, this free space as a fat file system, and then just create. Okay, so bare metal named partition 3 now, and that's a file and formatted as a fat. Okay, so now I will just go to the U-boot, just press Control C, and then again UMX 0, MMC 0. So now this time you will see there are three USB storages are mounted. The one was boot, one was root, and one is bare metal, which we just created partition right now using the disk utility. So actually we don't need to mount all those partitions. I need only partition 3. So I will use :3. Now only one partition will be mounted here. Okay, so bare metal. We will copy our dot bin binary file to here. So just go to your apps demo which we created in the build. You will see this demo.bin. Copy this, go here and paste this. After pasting, just hit Ctrl C because actual data transfer is happening. So for that, just close this and then eject. So in eject, our Linux ensures that all data is copied safely. And after that, if I hit ls, there is a command ls also. So U-boot is saying that you have to tell ls then interface MMC interface. Device is 0, partition is 3. If I enter, then you will see there is a demo.bin. Okay, so in MMC's partition 3 there is a demo.bin. Okay, so now how you will run this demo.bin binary file. So for that we will use the command fat load. Okay, so in fat load command they also give the how to use that. So in after fat load, then interface, which is MMC interface, device and partition, device 0 for internal, and partition 3. then address, at which address you want to copy the binary file. Now, as I showed that, wait, where was that? Yeah, we are copying our binary to this address. Okay, so the address will be 0x8, then 7 zeros, 1 2 3 1 2 3 4. And after that, a file name. What file? So file is demo.bin. Okay, and after that, how many bytes? We are not giving how many bytes because I want a whole file should be copied. So after enter, okay, now it is copied, the file is copied to this address. So I will jump my CPU using the go command to this address. So 0x8, then 70. So 1 2 3 1 2 3 4. So if I enter this, you will see hello from demo bare metal and application terminated. I come back to uboot. Uh, so our demo, the main.c was just a uart print string hello from demo bare metal. So our bare metal program is run successfully. In next video, I will talk about RTOS operating system. Uh, I mean little less operating system, which is RTOS. So I will tell about the RTOS. We will start from directly running the RTOS. I will not tell about the all this process again. This is the whole process to how we will run our bare metal program. Thank you.